So we continue our discussion on metamorphic rocks. Now, in this lecture, I would emphasize, so essentially when a rock, a system of rock or a mineral aggregate alters in response to changes in pressure, temperature and fluid composition imposed from outside, then the rock of course tries to find out the mineral assemblage that has the lowest free energy. For that, it's like an iteration, and obviously only those minerals at that particular pressure temperature, only those minerals with a particular composition where that make up the lowest free energy in the system become stable. Now, if this has to happen, therefore, when you're changing the pressure temperature condition, obviously different minerals become stable at different pressure temperature conditions. Now, different minerals become stable means old minerals that are there react to produce new minerals having a particular composition. And equilibrium means that there are no unstable phases, like we discussed before. Instability, there is no unstable minerals. It's in chemical equilibrium of stable minerals. So in order to attain the lower free energy, earlier minerals must or may need to change into new minerals so that the new assemblage has the minimum free energy value. Therefore, reactions are a very important part of metamorphism. Reactions are a very important part of metamorphism. So what happens now, these changes that occur in the stabilizations of different minerals as a function of changing pressure temperature, which is also a function of the time. So as the time changes on, metamorphic minerals obviously has to change to attain equilibrium which is consistent with the equilibrium at that particular pressure temperature condition. So metamorphic reactions become stable, and so this lecture I will try to focus on, is there a way to find out how different minerals at what time they form. That means I'm trying to find out the sequence of mineral growth as a function of time. So if I do that, time is not written on the rock. Time is not written on the rock. That time we need to find out. So the best, easiest way is to find out the relative time. That means whether this mineral formed early, this mineral was there before, etc., etc. So there has to be some markers in a rock, which give us an idea of time. That this feature formed early, this feature formed later, and so there is a mineral. Let's see how the mineral occurs with relation to these different markers. This will be the topic for this lecture. Now, metamorphic rocks normally are characterized by a planar arrangement of minerals, anisotropic minerals. This is a characteristic feature of a metamorphic rock. How it happens, let me tell you. There are essentially 4 types of metamorphic rocks: slates, phyllites, schist, and gneiss. These are the 4 mesoscopic varieties of rocks. Mesoscopic varieties. That means that is how they look, they are called. So you go to a field without doing anything, you say, okay, this is a slate, this is a phylite, this is a schist, and this is these. What are these? Now slate, normally you will know this rock. I don't know, of course in modern times young children do everything in computers, but when we grew up, there was a small board given to us on which we used to write with a chalk. And that board that was there, we used to put it on our lap or on the table and write. That was made of a dark material. If it fell, it broke. That is called a slate. So in fact, it is called a slate. So slate is a metamorphic rock, which is very dark, almost jet black in color. And the minerals in the slate, you will not be able to distinguish with your naked eye. You will not be able to distinguish. And they are brittle. That's why when you throw them, they break. And they have a very finely laminated habit. They are very fine laminations. But the laminations are non-separate. So it's a dark colored rock which is brittle in nature and which is characterized by a fine laminations of minerals. But the laminations are non-separate. That's a slate. I will talk about the lamination later on. These laminations that you see in a slate are formed by the parallel arrangement of anisotropic minerals. I will tell you a little more about it. In phyllite, also are made of very laminated rock, very finely laminated rock, but they are separate. I mean, if you take your nails and you scratch the broken part, you will see flakes of these rocks are coming out. They have a light, they have a sheen. They are not dull like the slates. Slates are very dull. But in phyllites, they are not dull. They develop some sort of a sheen-like thing, a polish, like if you have a boot and you generate and you give it a good polish, it has a sheen of itself. But the color is not black. The color is very light green, very light, very pale green sheen on the rock. This is a characteristic of a phyllite. And the laminations that you have are separate. In schist, but in a phyllitic rock, normally you will not be able to identify most of the minerals. Some minerals you will be able to identify using a lens. Using a lens you will be able to identify the minerals. But unlike slates you can't even identify it in the microscope. Sometimes even in the microscope it becomes difficult. But if you take the phyllite under a microscope and see with a higher power, you can see the mineral, identify the mineral, and with your naked eye, or using a lens, a hand lens, which has a magnification of 10x or 20x or something like that, you can identify some of the minerals. You can identify some of the minerals, not all of them. Schist is the next step, where you can identify almost all minerals with the naked eye. Most common minerals you will be able to identify with the naked eye if you have the experience. And if you hit with a hammer, they split open. If you hit with a hammer, they break easily. But they are not very hard rocks. They have an alternate arrangement of layers like this. This is dominated by micas. These are dominated by micas. You have sort of alternating layers of micas. And you have a layer which look like this, some sort of. And these are dominated mostly by quartz, but also some feldspars. These are the dominant minerals that you have. Not all schist, most of the schist is very common. Quartz and feldspar, most is quartz, or less feldspar. And the minerals are dominated by micas, and these are biotite, muscovite, chlorite. Now, I will not go into this. I am sure your mineralogy teacher must have been teaching this. But these are all very flaky minerals. They are listed under phyllosilicate. phyllosilicates. Unlike the minerals that are here, which is quartz and feldspar, these are tectosilicates. I told you this before. But you can take a small hammer, and if you hit, it will split off parallel to these laminations. It will split off. And then we come to the gneiss. Now these are much more hard rocks. They are very hard rocks. Normally if they fall, like you put a slate and you put it on the ground, just leave it, it will get shattered. The gneiss will not shatter. It will hurt your feet if the gneiss falls on your leg. It's a heavy rock. It's a hard rock. It also has a planar arrangement of minerals. But this time, in a gneiss, the quartzo-feldspathic layers, the quartz-feldspar layers, they are much more dominant. They are coarser. And the micaceous layers, they are much less. They are much less. Now, these four types of rocks are the dominant types of mesoscopically identifiable. Mesoscopic means in-hand specimen and rock. I can go to I said, okay, that is a slate, that's a phyllite, that's a schist, this is a gneiss. Without going into any details of it. You can, with experience, by the time you're in the final year, maybe the geology student, they will be able to identify it. Normally we do it in the laboratory class, but this time there's no laboratory class. So now, if I arrange the rock in terms of temperature, then temperature increases this way. That means slates are low temperature rocks. Phyllites are rocks that form at slightly higher temperatures. Schists are still higher temperatures. And the highest temperature rocks are gneiss. These are gneisses. This direction, the grain size increases. The grain size increases. And also broadly around this, micaceous layers are thinner. Relative to the quartz feldspar rich layers. Along this direction, the temperature increases. Because the temperature increases, rocks grow into larger grain sizes. And micaceous layers, which are dominant in phyllite schists, in the gneisses, they become less. So micaceous layers become relatively thinner relative to the quartzo-feldspathic layer in the quartzo-feldspathic gneisses. So this is about the mesoscale structures. These are the four identifiable mesoscale features of metamorphic rocks. There is another type of metamorphic rocks. It is called hornfells. This hornfells is a slightly different rock. So I will not discuss it along with slates, phyllites and schist, but I will make a mention later on. So just repeating, you have four mesoscale types: slate, phyllite, schist, gneiss. Grain size increases this way. Temperature increases this way. The micaceous nature of the rock, the thickness of the micaceous layer, they decrease this way. Now, in all these four types of rocks, if you look very carefully, either under the microscope or in hand specimen, you will see they have a planar arrangement. Whether it's a phyllite, whether it is a schist, they have a planar arrangement. So you will have micaceous layers normally, micaceous layers, and then you have quartzo-feldspathic layers. unlike sedimentary rocks that you have studied before, they have a difference. In the micaceous, these are also these that you are seeing, they sort of form a polygonal shape. Have you understood? They form a very polygonal shape. They form generally a polygonal shape. I'm not going into the details. And they have interlocking zones, so these rocks are quite hard, much harder than sedimentary rocks. So this is how the rock looks, interlocking, very polygonal crystals. Very polygonal crystals they have, unlike sedimentary rocks, which have more or less circular or angular. Here almost all grains are extremely angular. That's one thing. The other thing is, in this micaceous layers are mostly defined by anisotropic minerals. Anisotropic minerals. That means these anisotropic minerals, say for example, micas. You know, this is how a mica crystal looks like broadly. This is how a mica crystal looks like. So it is made up of very fine cleavages. Very fine cleavages. Then you have minerals like these are the cleavage planes. These are the cleavage planes. These have the orientation of 1 bar 1 0. These have the orientation of 1 1 0. 1 1 0. These are cleavage planes and these look like this. So they are longish in their size, and these are flattish in their size. There are other minerals which have a bladed form. So sometimes these minerals have some sort of a bladed form. A bladed form. Sometimes they have acicular forms, like a needle-shaped forms. Sometimes they are bladed. Sometimes they are very laminated. So these minerals define the cystosity. These minerals define the metamorphic fabrics. They define the metamorphic fabrics. Now, so essentially, you have in the metamorphic rock alternate mineral layers, mineralogically distinct layers. Quartz layers, quartz feldspar dominated layers, and mica dominated layers, or layers dominated by anisotropic minerals, like, say for example, this is a typical structure of a hornblende. Hornblende. They are not like, I don't know whether you know the garnet. It looks like a football. It has dodecahedron 12 shape. It's very much spherical in shape. So it is it's a very isotropic mineral. It does not have a preferred shape, a preferred alignment. A is equal to B is equal to C. It does not have an alignment as such. It does not have a length or a breadth which is prominent. No, it does not have. So these anisotropic minerals in micaceous rocks define the major fabric in this, the major fabric. So these are parallel alignment of this. Now, why does the alignment happen? Let me tell you that. Why does the alignment happen? Let's say you have a wall like this where you generate a shortening direction. So if the shortening direction is like this, your stretching direction is like this. It's at 90 degrees. So let's say in this case it's pure shear. What is pure shear? Where the shortening direction is at least a 90 degree to the shear zone wall. Have you understood? So as you apply pressure, this axis does not, the intensity increases, but it does not move, and this stretching direction accordingly increases. Now if there is a mineral, and say this is the third dimension, and this is the third dimension. So now, if a mica mineral is to form here, then the mica mineral will also form in this direction. With its cleavage, with its mica mineral will align itself with its cleavages like this. So what happens? The mica minerals with the flat face are aligned perpendicular to the maximum shortening direction, and the face is parallel to the direction of the maximum stretching. Have you understood? So the minerals align themselves in such a way, so these anisotropic minerals with differences in sizes, they align themselves in such a way that their larger faces are perpendicular to the shortening direction, or the mineral is parallel to the extension direction. Now say for example I have said about this, but if we take a case of say simple shear, even if it's a simple shear, let's say this way, then the maximum stretching direction is this way, and the maximum stretching direction is this way, and the major shortening direction is at 90 degrees to it. So what happens is, when these anisotropic minerals align, they align themselves like this. They will align themselves perpendicular to the shortening direction. Have you understood? So, while in simple shear, in this case, in a simple shear, the alignment of the mineral is oblique to the shear zone wall. This alignment is oblique to the shear zone wall. I drew earlier, it was also perpendicular to the shear zone. It was also perpendicular to the shortening direction. But in the pure shear, the one that I drew earlier, the pure shear was normal to the shear zone wall. And here it is at an angle to the shear zone wall. So for a simple shear, the foliations are aligned perpendicular to the shortening direction, of course, but they are aligned at an angle to the shear zone wall. But in pure shear, because the shortening in the earlier diagram, the shortening direction, since the pure shear direction is like this, so the minerals were aligned perpendicular and therefore parallel to the shear zone wall. So the orientation, therefore, the orientation of this alignment of the minerals, of the anisotropic minerals, this alignment of the anisotropic minerals, the angle between the shear zone wall and the foliation, that would vary depending upon how much pure shear and how much simple shear component is there during deformation. But the cardinal rule is it will form perpendicular to the direction of shortening. That is why all minerals are aligned like this. So that is the most important. See, this alignment of minerals in a metamorphic rock, is given by terms which are sometimes interchangeable, but some people use a different connotation. This is what is called the gneissic foliation, the schistose. The term that is used is foliation or cleavage. Foliation or cleavage. This is the term that is used to refer this parallel alignment of metamorphic minerals. Because most metamorphic minerals, all this, form due to some sort of a deformation acting on the rock. So this is either called metamorphic foliation or metamorphic cleavage. They form normal to the maximum shortening direction, but their alignment of the foliation will depend on the percentage of pure shear and simple shear component in the rock. So the alignment will depend on the strain pattern, but the mineral growth will be perpendicular to the shortening direction and therefore parallel to the stretching direction. This is a major difference. You see, sedimentary rocks also have bending, also have a bedding plane, but their minerals are not aligned like in metamorphic rocks. Have you understood? In metamorphic rock, they have a strong alignment because of the effect of stress acting on the rock. But in sedimentary rock, there is no such stress acting on the rock, as the intensity of this deformation is very high. So all metamorphic rocks most metamorphic rocks are characterized by a metamorphic foliation or a metamorphic cleavage, which is defined by the alignment, parallel alignment of shape-preferred aggregates of anisotropic minerals. The bedding plane of a sedimentary rock is very different. Now, the hornfels. In the hornfels, what happened? This happens not always, they are not associated with deformation. Hornfels, this particular metamorphic rock is formed by what is called contact heating. Say you have a sedimentary rock that is intruded by a granite, but there is no ongoing far-field stress acting on the rock to align the growing minerals. So what happens in hornfels? There is very little or no alignment of any metamorphic mineral. Have you understood? So that is very important. In hornfels, the minerals are more or less randomly oriented, or they may have a very weak alignment. Unlike slate, phyllite, schist, and gneiss, all of them have a very strong alignment. So metamorphic rocks, slates, phyllite, schist, gneiss are all characterized by a planar arrangement of anisotropic minerals. These alignment is as a result of stress. So these minerals align themselves perpendicular to the shortening direction and in the plane perpendicular to the shortening direction along that plane. That orientation of the plane may be parallel to the shear zone wall or may be at oblique to the shear zone wall, depending upon the pure and the simple shear component. But they are always perpendicular to the shortening direction. Right? And so we have come to what is to be known as metamorphic foliation or metamorphic cleavage. Sometimes for schistose rock, these are called schistosity plane. In gneissic rock, these are called gneissic planes, and so on. But essentially, that definition of a foliation in a metamorphic rock remains so. There are also different types of foliation. We do not need to understand all that in the first introductory lecture of earth science. Now, there is an important point here now I want to make. So, let's say I have a rock which has a foliation. Have you understood? So let's say I apply stress on the rock. So what will happen? This is the direction of stretching, this is the direction of shortening. So what will happen? They will start folding. This is how it will happen. So what is happening is, when you have a metamorphic rock with already a plane, metamorphic plane existing, or say for example a sedimentary rock with a bedding plane, and you apply stress onto the rock, what will happen? They will start to fold. Now what happens if you increase the intensity of deformation acting on it? Then what will happen? It will fold like that. They will fold like that. That means what is happening? The amplitude to wavelength ratio is changing. The amplitude to wavelength ratio is changing. As you apply more stress, the amplitude increases and the wavelength of the pole of that layer decreases. So essentially, amplitude by wavelength ratio increases. Now what happens is, you can see here what I have drawn, or even here what I have drawn, or even here what I have drawn, and even here what I have drawn. When I do this, what happens is, if I apply stress on this direction, shortening, then the stretching is on this side. So what happens is, the foliation planes, they crowd closer. They crowd closer, and materials from here migrate more towards this side. So this is called the limb of the fold, and this is called the hinge of the fold. So what happens? In the hinge area, the foliations becomes more spaced, and in the limb area, they become more crowded. Have you understood? This variation accentuates as you apply more and more stress on the rock. Till what happens is, this is what happens. What happens is, perpendicular to the shortening direction, a new foliation develops. A new foliation develops, or a new cleavage develops. This was the older foliation. Older foliation. This is older. This is younger. Have you understood? So now you have got two cleavages. This is an older foliation cleavage, and this is a younger foliation cleavage. This is called a crenulation cleavage. This is called a crenulation cleavage. And this is called crenulated cleavage. This is crenulated cleavage, so you will see small hinges, and suddenly you will see this fabric. as you continue this, what happens is, if you continue this deformation, then this is what will happen. Eventually, this is the older cleavage, and this is the crenulation cleavage. Have you understood? This then is the crenulation cleavage. These ones are the new cleavages formed at 90 degree to the pure shape of color. And these hinges are now almost being obliterated because of the intensity of deformation. And you can imagine what will happen at one point of time, at the end stage of this, you will have a foliation like this. And the earlier foliation almost gone. Or maybe this will tell you that the rock, always you will see this, and you will not even know whether there was a fabric before, foliation before. But this will tell you, there was a fabric before. There was a fabric before. Why is it important? It's important very much because this is older and this is younger. So it gives you a time relationship. It gives you a time relationship. Have you understood? That is the most important thing. So this is younger, this is older. This is earlier, this is younger. That means you now get in the rock a marker by which you can say, okay, this is older, this is younger, this is older, this is younger, this is older, this is younger. So you know which parts are younger in a rock and which parts are older in a rock. This you know. So it gives you it gives you an idea, not of the absolute value of time, but a relative sense of time. It gives you a relative time frame in which to find out the sequence of mineral growth. And that is why it is very important to have these structures still preserved. But and this is, you can see here, you started with this orientation and you ended up with a normal orientation. This orientation was produced because of some earlier shortening event. This event that produced the foliation was of this orientation. Yes or no? This was applied on this schistosity. This is later. This is the same applied forces. So now that you see it is normal to the shortening direction. But originally, before, when we started with this, the original stress directions were different. Now you can extrapolate this to a mountain building, say in the Himalayas. In the Himalayas, most of the foliation are towards north. Most of the foliations are north dipping and very gentle. That means obviously you can find out which direction was the stress field that produced the Himalayas. Have you understood? So that is important in geology and metamorphic petrology, you can go from the minutest scale to the largest scale possible by extrapolating it, by investigating small samples across the Himalayas. You can find out how Himalayans evolved. How did the stress fields vary? And if you can find out the stress field vary, then how was the tectonics that is happening? That happened at some point of time. And this you can extend it to very old mountain ranges, very old subduction zones. You can find out and decode it. That, okay, this is possibly what is happening. Now we come to another important issue. So we understand now that different fabrics can be identified in a rock, and these different fabrics give you an idea of time relationship in a rock in relative scale, not on an absolute scale. We will not have the option of discussing that. That can also be found out, but I don't think at your stage it's necessary that you should know. You should first be focused on the basics and then move on, rather than doing fantasy things and not understanding the basics. Now, in our next step, we will talk about a little bit about mineral growth in relation to fabric, in relation to metamorphic foliation. Let us talk about this topic for a little while, and I think as I extrapolate my lecture, I will not be able to finish metamorphism today. In this lecture, we will have to continue for the next time. So as well, I don't rush it up, I try to do as best. We will now try to find out how mineral growth can be identified in relation to metamorphic foliation. We will first do the simple things first. Say, for example, in a rock there are minerals which you have been hearing for a long time. Now, many of the minerals, say micas, these are very soft minerals. Soft minerals means they can slip past one another very well. But there are minerals which don't allow slippage so easily. Have you understood? They are more rigid. They don't slip easily. Similarly, there are minerals, some minerals get deformed, but there are minerals which do not get deformed. They are very strong, rheologically very strong minerals. And there are these strong minerals, they are found out to deform plastically or deform in a ductile manner at a higher temperature. So there are great complications. All minerals do not have the same strength. Micas are weak. Quartz and feldspar are much stronger. A mineral called garnet, this mineral you must have heard several times. Garnet, which actually looks like a sphere with a very good dodecahedral face. 110 is the plane. It's a type, in the isometric system it occurs. It's an isometric system. It's a normal class. Dodecahedron belongs to that, where you have 12 crystal faces arranged almost like a sphere, and each face is 110, which is the classic dodecahedron shape of an isometric system. Dodecahedral class. So now what happens is, all minerals do not have the same strength. Garnet, for example, is very strong. There are minerals like zircon, ZrSiO4, very strong. They don't deform. They don't deform easily. Only at very high temperature they can deform. Otherwise they don't deform. So if you have a rock where you have a garnet and a mica, what will happen? And if you apply stress to a rock, the garnet will remain rigid like a circle, and the micas will flow around it. Have you understood? The micas will flow around it because they are weak. Okay. Similarly, quartz and feldspars, if the temperatures are high, reasonably high enough, around quartz plastically deforms at 200 degrees centigrade. Feldspars plastically deform at around 400, 450 degrees centigrade. Garnet plastically deforms at temperatures above 800 degrees centigrade. Have you understood? So if you have a rock characteristics with different strengths, you would expect during a stress field that the strong minerals won't change their shape or size, and the softest mineral will take the major amount of flow. So if there is a pure shear, deformation is divided into pure shear and simple shear. Simple shear means moving a pack of cards, sheathing. And pure shear is where you have this situation. I told you before also, rotational, non-rotational shear and rotational shear. Here there is rotation around this. Here there is no rotation. A circle becomes an ellipse. Here there is rotation. So this is a rotational shear, this is a non-rotational shear. Now if you apply this, if there is a mineral like mica, which are very weak, they will accommodate much of the simple shear component. They are most likely to accommodate the slips because of simple shear. And the pure shear component will be accommodated by other minerals. That means if there is a bulk strain, stress acting on the rock, micas will accommodate the simple shear component much, much better than the quartz and feldspar grain, which does not slip very much. They will accommodate the pure shear component. So what happens is, for a bulk strain, the strain is partitioned. The strain is partitioned. Micas, if there are, would take up a bulk of the simple shear or rotational shear, whereas the quartz and feldspars and the garnets, which are rigid, they will take up much more of the pure shear component. Okay? I think I will stop here because I think if I start the next one, it will take some time. Okay, we will then take it one more class to finish metamorphic metrology. Thank you now.